Hello viewers, in our previous lesson we learned that associated with every event there is always a random experiment. For example, to study the chance or probability of getting an odd number in a cubical die or a perfect die, the experiment is throwing a die and study the number or observe the number shown on it. The set of all possible outcomes in a random experiment constitute the sample space. So, the sample space for this random experiment, which is throwing a die, has the outcomes 1, 2, 3, 4, 5 and 6. As we learned in our previous lesson again that an event is a subset of the sample space defined under definite rules or described by a statement. The event for this particular random experiment has been described by the statement getting an odd number. Now, if we ask the question that is the number shown odd, if the answer is no, then we say that the event has not occurred. In case the answer is yes, then we say that the event has occurred and we consider that outcome as the favorable outcome. The set of all favorable outcomes makes the event set. So, the event set for this event, that is getting an odd number, has the favorable outcomes 1, 3 and 5. We can show this by Venn diagram as this is the sample space and this is the subset which is defining the event getting an odd number. If I define this event as A, then it has the outcomes 1, 3 and 5, and rest of the outcomes are left out in the sample space. They are 2, 4 and 6. The probability of an event depends on the number of favorable outcomes and the total number of equally likely outcomes. To illustrate this, here are two balls inside this container. They are exactly similar, but one is blue and the other is pink. If I pick one ball at random from this container, then what is the probability that the ball which has been picked up is a pink ball? Now, as we can see, since there were two balls inside this container, so the number of equally likely outcomes for this random experiment were 2. So, the sample space had 2 elements and the favorable outcome is only 1, and therefore, the probability of picking up a pink ball will be 1 upon 2. But what happens if we increase the number of pink balls in this container? Now, in this container now we have 3 pink balls and 1 blue ball. Therefore, the sample space for this random experiment will have 4 outcomes, 3 pink balls and 1 blue ball. But the favorable outcomes are 3 for this event, that is picking up a pink ball, and therefore, the probability of picking up a pink ball will be 3 upon 4, which is a much larger fraction than the fraction 1 upon 2, which was the probability when there were only 2 balls. Now, suppose I increase the number of blue balls inside this container. So, now we have 1 pink ball and 3 blue balls inside this container, the experiment is picking up one ball at random. So, the sample space will have 4 outcomes, but the event is picking up a pink ball from this container. So, the favorable outcome will be only 1. This gives the probability of picking up a pink ball from this container now will be 1 upon 4, which is a much smaller fraction than the original probability, that was 1 upon 2. Thus, we can generalize that if the number of favorable outcomes for an event is increased, then the probability of occurrence for that event increases, and if the number of favorable outcome is decreased, then the probability for the occurrence of an event decreases. Now, coming back to this experiment, that is throwing a die, the probability of the event, that is getting an odd number, is given by the number of favorable outcomes upon the total number of equally likely outcomes. In this experiment, the favorable outcomes is 3 and the number of equally likely outcomes is 6. So, we get the probability as 1 upon 2. The outcomes in the sample space are also called elementary events. A number of events may be defined associated with a random experiment. For example, if we take the random experiment as throwing a die, and the sample space, as we know, has the outcomes here 1, 2, 3, 4, 5 and 6. Now, let us define an event here, that is getting an even number. If we define this event as E, then it has the favorable outcomes 2, 4 and 6. Another event F may be defined as getting a number less than 3. So, it will have the outcomes 1 and 2. A third event may be defined as getting a number greater than 3. So, it will have the outcomes 4, 5 and 6. We can also define events by combining any two of these events. For example, we can define an event E or F, which is said to occur when E occurs or F occurs or both E and F occurs. In other words, we can say that when at least one of these occurs, then we say that the event E or F has occurred. Now, let us find out the subset for this event E or F. We know that the event E is defined by the subset having the elements 2, 4 and 6. Event F has the outcomes 1 and 2, and therefore, the subset for the event E or F will be E union F, which will have the outcomes 2, 4, 6 union 1 and 2. So, this gives us the set 1, 2, 4 and 6. In Venn diagram, we can show this as, if this is the sample space, then the event E or F, if this is the event E, this is the event F, is shown like this. Therefore, probability of the event E or F will be given by the number of favorable outcomes for this event E or F, which is given by the set E union F. It has 4 elements, so it is given by 4 upon the total number of outcomes in the sample space, which is equal to 6. So, this is equal to 2 upon 3. Similarly, event E or G occurs when E occurs or G occurs or both E and G occurs. So, the subset for the event E or G is given by E union G, which has the elements 2, 4, 6, union 4, 5 and 6. So, we get the final set E union G as 2, 4, 5 and 6, that means it has 4 elements. Again, by Venn diagram we can show the set E union G as, if this is the sample space, then this is the set E, this is the set G, and since both this set have 2 elements common, I can write 4 and 6 here. The union is given by the 2 sets here, and therefore, probability of the event E or G is given by the number of favorable outcomes for this event, which are 4 upon the total number of equally likely outcomes in the sample space, which is 6. So, it is again equal to 2 by 3. We can also define an event E and F, which is said to occur when both E and F occurs together, that is, the outcome belongs to E and F together. So, event E and F occurs when the event E occurs as well as the event F occurs, and therefore, the subset for the event E and F is given by E intersection F, which is 2, 4, 6 intersection 1 and 2, which is equal to 2, because the common element in these 2 sets is 2. By Venn diagram, we can show this event E intersection F as, if this is the sample space S, this is set E and this is set F. This portion defines the event E intersection F, which has the element 2. Therefore, probability of the event E and F is equal to the number of favorable outcomes for this event E intersection F, which is 1 upon the total number of outcomes in the sample space, which is equal to 6. Similarly, we can say that the event F and G occurs when both F as well as G occurs together. So, the subset is defined by F intersection G, which is equal to 1, 2 intersection 4, 5 and 6. As we can see, we do not have any element common in these 2 sets. So, the final set F intersection G which we get is a null set. By Venn diagram, we can show it like this. This is the sample space, this is set F and this is set G. They do not have any common element, and therefore, probability of the event F and G is equal to the number of favorable outcomes, which is 0 in this case, upon the outcomes in the sample space, which is 6, which is equal to 0. The events E, F and G are called elementary events, and the events E or F, E or G, E and F, they are examples of decomposable or compound events. We now try to establish a relationship between elementary events and compound events. For that, let us again observe these events. The first event, that was event E, was getting an even number in the random experiment through a die. The second event was getting a number less than 3, and the third event, that is event G, is getting a number greater than 3. Now, if we get a number 2 on a die, then we can say that both event E as well as F has occurred together. Now, consider the events F and G. Can these two events occur together? When F occurs, that is when we get a number less than 3, then it cannot be a number greater than 3. That means event G cannot occur. On the other hand, when event G occurs, that means when we get a number greater than 3 on a die, then it cannot be a number less than 3, which implies that event F cannot occur. Such events are called mutually exclusive events. We can show it by a Venn diagram like this. If this is the sample space, then if this is the event F and this is event G, we say that events F and G are mutually exclusive because the occurrence of one excludes the occurrence of the other, or we say that the event F intersection event G is a null set. So, two sets A and B are said to be mutually exclusive if occurrence of one event, that is if the occurrence of the set A excludes the occurrence of the event described by the set B. So, can you say about events E and F, are they mutually exclusive? No, since we have seen that they have a common element 2 between them, and therefore, they are not mutually exclusive events. So, we say that if two events have a common element between them, then they are called not mutually exclusive events. Now, consider the experiment. Drawing a card from an ordinary pack of cards. So, this is an ordinary pack of cards and the experiment is drawing a card from this pack of cards. Now, since there are 52 cards in this pack of cards, so any one of these cards can be the likely outcome when we pick up one card at random. So, the sample space has 52 outcomes. Now, let us say that the event A is described as the card is a heart, event B, let us take it as the card is a king, and event C as the card is a spade. Now, consider events A and B. Event A is the card is a heart and event B is a card is a king. Now, if we get a card which is the king of hearts, then we say that the event A as well as the event B has occurred together. So, the event A and B are not mutually exclusive events. Now, consider the event A and C. Event A is getting a card which is a heart and event C is the card is a spade. Are they mutually exclusive? When we get a heart from this pack of cards, then it cannot be a spade. On the other hand, if we draw a spade from this pack of cards, then it cannot be a heart. So, we say that the events A and C are mutually exclusive. At times we know the probability of an elementary event, but how can we find the probability of a compound event? Let us try to find a relationship. If A and B are two mutually exclusive events, then what is the probability of the event A or B in terms of the elementary events? Now, as we are given that A and B are mutually exclusive events, that means they are disjoint sets, and therefore, the number of elements in the set A union B is given by the number of elements in the set A plus the number of elements in the set B. Now, let us suppose that the number of elements in the set A is P, in set B it is Q, and the total number of elements in the sample space is N. Therefore, the probability of the event A or B, where A and B are mutually exclusive events, will be given by, it is same as probability of the event A union B. This is equal to the number of favorable outcomes for this event A union B, or for this set A union B. Now, set A union B has P plus Q elements upon the total number of equally likely outcomes in the sample space, which is equal to N. Now, this is equal to P upon N plus Q upon N. What is P upon N? P upon N is the probability of the event A, and Q upon N is the probability of the event B. So, we can write this as P of A plus P of B. Thus, we get that if A and B are two mutually exclusive events, then probability of an event A or B is given by P of A plus P of B. This result is called addition theorem on probability. This theorem can be extended to a number of mutually exclusive events E1, E2, E3 to En. We have probability of E1 or E2 or En is equal to probability of E1 plus probability of E2 plus probability of E3. So, till En, which is given by summation of I going from 1 to n probability of Ei. Now, in case the events are not mutually exclusive, then the probability of event A or B in terms of the elementary event, we take it like this. This is the Venn diagram where the set A and B, or the events A and B, are not mutually exclusive. So, this space, that is the shaded portion, shows the intersection or the common portion. Hence, we have number of elements in the set A union B is equal to number of elements in the set A plus n of B minus n of A intersection B, and therefore, probability of A or B when the sets A and B are not mutually exclusive is equal to probability of A union B, which is equal to P. Let us suppose that P is the number of element in the set A, Q is the number of element in the set B, and R is the number of element in the set A intersection B, defined by this shaded portion. So, P plus Q minus R, we get it from here, upon N, which is equal to P upon N plus Q upon N minus r upon n. This is equal to probability of the event A plus probability of the event B minus probability of the event A intersection B. So, this is another result, addition theorem on probability for not mutually exclusive events. Now, let us take a problem. A card is drawn at random from a pack of ordinary cards. What is the probability that the card drawn is a red card or a king, a queen or an ace? Now, we know that in an ordinary pack of cards there are 52 cards. So, each one of these cards can be equally likely outcome if we pick up one card at random. Therefore, the sample space for this experiment has 52 outcomes. Now, our first event is getting a red card and a king card. So, let us define event A as the card drawn is a king. Since there are only 4 king in a pack of cards, so the number of elements in the set A will be equal to 4, and therefore, probability of the event A is given by 4 upon 52, where 52 is the number of elements in the sample space and 4 is the number of favorable outcomes. Now, again let us define event B as the card drawn is a red. Now, since there are 26 red cards, therefore, the number of elements in the set B will be equal to 26 and probability of B will be 26 upon 52. Now, in a pack of cards we have 2 cards which are red and king. They are king as well as red. So, 2 events are occurring together. So, the set N intersection B will have 2 elements and therefore, probability of the event A and B will be equal to 2 upon 52. Now, are the 2 sets mutually exclusive? No, they are not, because we have already seen that the 2 sets, that is the first event getting a card which is a king and the second event that is card is a red, they have 2 common cards which is a king as well as a red card, and therefore, applying the result, that is addition theorem on probability for not mutually exclusive events, we get P of A or B is equal to P of A plus P of B minus P of A and B. P of A is equal to 4 upon 52 plus P of B is 26 upon 52 minus P of A and B is 2 upon 52. So, this is equal to 28 upon 52, which can be further simplified, and we get the probability of the event A or B as 7 upon 13. Now, for the next event, that is the card drawn is a queen or an ace. Now, again the sample space has 52 outcomes. Let us define event C as the card drawn is a queen. So, the number of elements in the set C will be 4 and probability of the event C will be given by 4 upon 52. Let us define the event the card drawn is an ace as D. So, number of elements in the set D will be again 4 and probability of the event D will be again 4 upon 52. These 2 events are mutually exclusive, and therefore, using the result for mutually exclusive events, the probability of event A or B is given by probability of A plus probability of B, which is equal to 4 upon 52 plus again 4 upon 52. This is equal to 8 upon 52, which is equal to 2 upon 13. Thank you.